And with that, we will begin. As I said, Monday, if you have any questions, feel free to just yell out, or if you want to type them up, let's do that. Don't be shy. All right, so what we did on Tuesday, I don't know why I said Monday, Tuesday. So last class, what we talked about was the so-called mean or expected value of what's called a random variable. So that was kind of the big topic of last class. We did an example. I posted some homework that hopefully you guys will or have at least attempted. I don't know. If you look at the homework, that's what the problems are dealing with. Does anybody have any questions about the homework? Someone does. Yeah, so someone said the homework was confusing. Yeah, some of it should be right now. We didn't necessarily cover each one of those topics yet. We're going to do some of that today. So perhaps what we can do is we're going to start with some examples, and hopefully that makes it a little less confusing. Basically, the first few questions in the homework are something that you can Google, or you should if you read in the book. Don't forget, there's a version of the book. I put in a digital version of it on Canvas right next to the syllabus. So you guys all have access to that. Just don't tell the authorities it's there, so they'll sue us. But you can read that. And also you can just Google these terms. You can Google discrete, continuous. I didn't really speak about them in class because for us in a level of class like this, it's not that important. But you should be aware of the terms. And that's why I'm basically just asking you to write them down. Problems 4 and 5 we actually did in class together. We did the probability distribution for a coin. It might be worth us going over that again to see exactly what we mean by that. So let's do that. We'll do it slightly different though, so you have something to match when you're doing your own homework. So let's look at an example. So let's word it exactly the same. So let's construct a probability distribution for the following experiment. So what we want to do is we want to toss a coin. Let's use 4 times. And count the heads. So that's essentially problem number 4. Now we've done this before, but it's worth doing again because if you look back at the homework, what you'll notice is we've talked about this problem in homework, and we've also done it in class, and we've sort of looked at it from a few different perspectives. So let's sort of look at it from this perspective. So here's the solution. So let capital X equal the number of heads. So here's what you need to note. How many values can X be equal to? So if we're only tossing a coin, then X can equal one of four things. It can equal 0 heads. X could equal 1. X can equal 2. X could equal 3. And X could equal 4. That is it. Those are all the outcomes. I have 4 outcomes of this experiment. Or excuse me, I guess technically you have 5. So now, does anybody have a question about to this point? All right. So what we'd like to note is, what is a probability distribution? Well, a probability distribution is a function that takes outcomes and assigns a number to them. And we call it a probability distribution because we want that function to assign the probability. So, for example, we want a probability distribution is only useful to us if it makes intuitive sense. So we want the function that tells us what's the probability we get 0 heads, or the probability we get 1 head, the probability we get 2 heads, etc. Now, you could write all these out if you wanted to. You can write heads, 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 and then heads, 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 tails. We've done that in class. But at some point, that's unnecessary because you've done it enough times and you've noticed that there are some symmetry. So let's head to the next page and think about this. So recall that the probability that X equals, say, 0 is what? Well, think about this for a second. Use a symmetry argument. If I ask myself how many times or how many different ways can I get 4 heads? Well, the only way to get 4 heads is if I get a head each time. So that is just one of the outcomes. And the only way to get no heads is if I get all tails. So the probability that I get 0 heads must be equal to the probability that I get 4 heads. And again, if you're a little confused why that's the case, well, this is the case because tails, 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 and heads, 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 heads each occur once. Also, so what this argument is I'm using deductive reasoning. I'm using some, what we might call symmetry arguments. Also, the probability that you get 2 heads exactly is the same as the probability of what? Let's just say tails equals 2. So what I'm trying to do is I'm trying to cut down on the amount of work I have to do.
Mm-hmm.
Now, another piece of symmetry that you can use is, now look, you don't have to do it this way. You can go back to one of the previous homeworks where we did this, and you can write out all 16 outcomes. There's going to be 16 outcomes. Why? Because I have 4 coins. Each coin has 2 options. So you get 2 to the 4th, which is 16 outcomes. But what I'd like to do is reason what they are without actually having to compute it. So for example, what is the probability of X being equal to 1? Well, getting 1 head is the same as getting 3 tails. But notice, getting 3 tails, since heads and tails are equally likely, this is the same as the probability of x equals 2. And of course, this is the probability of x equals 3. Getting 3 tails is no different than getting 3 heads. They're both equally likely. And so if we do this, we can conclude the following. So let's make a table. We can make sort of like a function table. What are the values of x and what are their probabilities? So there's 1, there's 0, there's 1, there's 2, there's 3, and there's 4 times or ways we can get heads. We know that getting this is going to be 1/16. We know that getting 4 heads is 1/16. And then we know that the guys in the middle have to have some pattern. They have to have a symmetry. So you ask yourself, what are the ways in which I can get 1 head? Or what are the ways in which I can get 3 heads? Because once you compute 1, the pattern is going to be evident by what we call symmetry. So the other thing that's easy to piece together is you know that all these fractions you're going to write down have to add up to 16. So another way to do this is you know each one of these is a fraction whose denominator is 16. And the only question now is how do you fill in these numerators? Now, you could, again, go and write everything out, but you've already done that before. Does anybody have any thoughts or questions or want to spit out the answer?
Would it be 3, 8, and then 3?
Okay, so you could check. Would it be 3, 8, and 3? Well, if you just do an initial test, how many different ways can you get 1 heads? It's not going to be 3 8s. Why? Because 1 head means you have 4 options for it. So you can have it the first toss, or the second toss, the third, or the fourth. So actually, it's not 1/8, it's what? Excuse me, it's not 3 8s, it's 4 8s. Yeah. It's going to be 4 8s for this. Or excuse me, 4/16, which is 1/4. And this is going to be, I keep writing this incorrectly. So if we use that reasoning, our intuition might tell us right away that it's, what is this stuff? That it's 4. Again, where do I get the number 4 from? Well, if I get exactly 1 head, that happens when it's the first guy or the second, the third, or the fourth toss. So that there's 4 situations there. So I have 4 out of the 16. And the same thing with the other guy. Now, 2 heads, how can that happen? Well, you can either reason it yourself or you can say, oh, there's 9 and then there's 7 left. So you might reason that this has to be 7. Or not 7, but if you check your math, this has to be 4 and 4 is 8. And then 2 is 10. So we reason that perhaps this has to be 6. And actually, if you drew everything out, you would convince yourself that this is in fact correct. So I'll let you think about that for a second. And perhaps you have a better way of actually going about it. Does anybody have a question while you think about it? Any quick questions? So again, if you're not sure, write out all the outcomes where you get exactly 2 heads, and you'll see that there's 6 of them. Again, you could write it all out if you want, but we should be confident that this is correct because all these numbers add up to 1. If I add all these fractions up, I get 16 over 16 is what I'm supposed to get. So this is one way to describe the probability distribution. This is one way to obtain it. There's other ways to obtain it. Any other questions before we move on? All right, so let's note that sometimes you can write this a little differently. So alternatively, we might write as a function. We might say f of x, which is the probability. Let's use a different letter so it's not so scary. I don't want to use x multiple times. So let's use, I think we used in class, we used this Greek letter omega, or let's just use, we think of it as a w. So what is this? Well, this is the probability that x equals some value. And we could write this as a function. So what are the outcomes? This could be equal to 1/16. It can be equal to 4/16. It can be equal to 6/16. It can be equal to 4/16 or 1/16. So we write this using what you guys would have called a piecewise function. And when is it equal to this? It's equal to this if w equals 0, w equals 1, w equals 2, w equals 3, w equals 4. So one of the hard things here is all the abstract language. That's what's going to give us a little bit of a headache. You got to, this is kind of like where you just got to take a deep breath and say, I ain't afraid of it. I know that's easier said than done, but. So there's 2 ways to sort of describe this probability distribution. This way, like this is sort of like a more abstract function way, or you can draw it or write it out like I did at the bottom of this page, sort of just like a little chart. In either case, what you see is you see a probability being associated with an outcome, or more particularly a random variable. Does anybody have a question about this? All right. I see someone's yapping. Where the hell did my chat thing go? Give me a second to find my chat. Disappeared. It does look scary. There's no doubt. You see, there we go. Now we're having fun. See, what good is this? I made it. Look, don't you remember? None of you can fail now. We've made this as great for everybody as possible. All right. So, uh-oh. Is that a dog or is that like a fox? You guys are, no one's going to laugh today? What I'd like to know is how many people who are logged on are actually there.
I'm here.
I know. I'm just kidding.
That's.
I have a feeling if it were me on the other side, I would just, I would probably take a nap. No, I'm just kidding. All right. So someone asked to do another one. Absolutely. Let's do, let's do this. Let's do it again for something different though. So I don't want to go immediately to a difficult problem, but if you look at the homework, if you have it in front of you or on the computer, You'll notice that problem 6 and 7, I gave you the probability distribution. I didn't actually ask you to find it. I'm giving it to you for some specific, you know, experiment or some specific study. So let's do another example where we have to construct a probability distribution. Let's see. Let's think about, I'm trying to think of a good example here. All right, here we go. So let's do another example. So construct a probability distribution for rolling 2 dice and counting let's say or so we're going to roll dice and counting the even. Okay, let's put it a little differently. I want to make this a little more accessible. I don't want to make it too difficult. So let's say rolling 2 dice 3 times and counting the number of 5s. So let's clear make this clear. So I'm going to take 2 dice and I'm going to roll it. If I get a 5, I count it. If I don't count it. Then I roll it again if I get a 5. So what are my outcomes? My outcomes are x equals the number of 5. So x can equal 0, 1, 2, or 3. Because I'm rolling it 3 times, I can get 1 5, I can get 2 5s, I can get 3 5s, or I can get no 5s. So let's see if we can reason this without drawing out the so-called outcomes. Now, we've asked you to study the dice before. And even though you've done it on a few homeworks, even if you don't have it in your brain, that's fine. You can easily just Google sample space of dice and you're going to find a picture. I'll show you that in a second. So what we need to figure out are these probabilities. So don't forget, I know this is something it's overwhelming a little bit for those of us who are not like used to taking math, but what do these scary symbols mean? If I write, let me change my pen color and let me remind you how to interpret this. And this is something I asked you to do in the homework just to build some confidence. So don't forget the way you read this. This reads, If I can only write on this. One of these days, I'm going to get real good at writing on this pad. So this reads the probability. I still can't spell. Who wants to take over for me?
Not me.
Why not?
Why would I?
Why not? You could get paid. So the probability we toss 3 5s. That's how you can read this. And then the one where it's x equals 2, that's the probability you toss 2 5s, etc. Need some water.
No rock star today.
Oh, don't worry, Liam. It's here, bro. Look, why would I leave home without it? It's here. Okay, so let's think about the probabilities of these things happening. So what's the probability you don't roll a 5 on the first time? Well, remember, we can think of each step of this experiment as one step at a time. So what's the probability you do not roll a 5? Well, rolling a 5 is 1/5, correct? So not rolling a 5 would be, we're going to have to think about this for a little bit. Probability of getting no 5s would be, okay, so you get everything but a 5. So if I roll 2 dice, how do I get a 5? I get a 5 whether it's what? I get a 5 if it's 2 and 3. I get a 5 if it's 3 and 2. Then I get a 5 if it's 1 and 4, 4 and 1. So there's 4 ways. Is there any other ways to get a 5? So it looks like at first the 5 is 4 out of 36. Now, let me pull something up because it might be useful for you to see this. So you get where the numbers are. So let's see if I can get a good image of this. Okay, here's a good picture. So give me a second. I'm going to share a picture with you. Hopefully it makes sense here. Do you guys see a picture with some web pages on it? Yes, no?
Yeah.
I do.
Yeah, okay. So if you look at this thing on the right, this is a sample space of rolling a dice or a pair of dice. So how do I get a 5? Well, I get a 5 if I have a 2 and a 3. I get a 5 if I have a 3 and a 2. So let me actually write this a little differently. How do I get a 5? I get a 5 here. I get a 5 here, here, and here. Well, that was actually not one. The way I get a 5 is 4 ways. I get it if I have a 4 and a 1, and a 1 and a 4. I get it if I have a 3 and a 2 and a 3. So that means 4 out of the 36 outcomes are going to be 5s. So if I go back to the whiteboard, if 4 of them are 5s, that means the other 32 are not. So 32 over 36 is the probability I do not get a 5 on the first roll. And then if I have 3 rolls, I have 32 over 36 times 32 over 36. So what is that for shorthand? That is 32 over 36 cubed. again, the probability, if you want to think of this in a more useful way, if I sort of annotate this up here. So this would be, this is your first. That's kind of very sloppy. So how can I, this is the first toss. Second toss. Third toss. So remember, I take all three of them and multiply them together. So it's 32 over 36. Now, using that symmetry argument, we can easily do the probability that I get 3 5s. Because that's going to be the opposite. That's going to be the probability of getting a 5 is 436. So this is 436 times 436 times 436, which is 4 over 36 to the power 3. So those were the easy ones because it wasn't hard to compute the probability of, getting a 5 or not getting a 5. Does anybody have a question about this? This is fun. Now, let me reiterate, it's not wrong for you to draw out and write out the whole sample space, but that is wasted time if you don't need to. Who has a question? Who wants to talk about life? Should we just give everybody A's and say no more probability?
Yes.
Yeah, I wish.
Good idea.
I'm at least saying you can all get C's.
So just give us C's and call it a day.
I mean, I'll take a B.
Liam, you don't want an A? What the hell?
I'm down for a B. Yeah.
Like, give us a B and call it a day.
No, I can't give B's. I'll give C's away, but you're gonna have to earn A's and B's, unfortunately.
All right, that's fair.
That's fair.
All right, let's do these other two ones. Let me erase this stuff that I wrote since it's in the way. So again, this is not. I'm not pretending this is easy, by the way. I'm merely sort of emphasizing that it can be done. I don't know that many people will learn this in 5 minutes. I think if you really want to learn this, it's going to take some effort on your part. Okay, so now let's think about what's happening in the next cases, because these ones we have to do a little thinking. Now, how can I get just 1 5? Well, that means I can get it on the first roll, I can get it on the second roll, or I can get it on the third roll. So let's assume I get it on the first roll. If I get it on the first roll, my 1 5 is 4 over 36, and then that means I don't get it on the second roll or the third roll. But that's that scenario. What happens if it happens on the second roll? Well, then it would be missed on the first, got it on the second, but missed it on the third. And then, of course, we also have the chance that that happens on, I get it on the third time, which means I missed, I got it. So you see, this is quite ugly now. I have 3 different scenarios to consider. Does anybody have a question about how I reasoned that? So a good way to think about this is think about success and failure. If I look at, if you can see my pen hovering over, here I have the success on the first, failure, failure. Then I have failure, success, failure. And then the third scenario is I have failure, failure, success. Now notice the same numbers keep popping up, so there's some shorthand for this if we wanted. And we're actually gonna learn an easier way to do this before the end of the class. So maybe you'll, I don't know if it's easier, but it's a quicker way. And some of you may already know what this is. We're kind of, what I'm trying to do through an example is motivate something called the binomial distribution, which makes this very easy to do. All right, does anybody have a question about this? Yikes. All right, so we can write out what that is though, if we want to. This is the same number written 3 different ways. So what I'd like to do is I would like to say, okay, you can write this for short. Let's go out in front and let's, I need to find space. So let's put it right here. I want to sort of, I don't want this to be connected with this. So what is this thing? A better way of, a more concise way, I should say, of writing this is, what is this? This is 3 times 4 to the over 16 times 32 over 16 squared. Because there's 3 copies of it. Wowzers. Take a deep breath. Contemplate life. Because we didn't even do the third one yet. All right. So the third one's going to be even longer, so we'll put this on the next page. Does anybody have a question before I move to the next page? By the way, I guess I should make sure you guys understand that this inside the green is not to be confused with this. All right, so let's suffer the torture of doing the probability that we get 2, or we roll a 5 twice. So the probability, my blue. The probability that I get 2 5s. Okay, so let's imagine I get them on the first 2 tosses. So that would be 4 32s, 4 32s. And then I don't get, oh, not 32, 36s. Heavens to Betsy. Okay, that's when I get them on the first 2. Then another scenario is I get it on the first try, miss it on the second try, but then I get it again on the third try. And then what's the last scenario? The last scenario is if I miss on the first try, and then I follow it up with a 5 and a 5. So let's annotate this. So maybe when you go back, because I know you're all great students and you're going to go back and study this example. So if I take a different color, So what does this mean? This means I get a 5 on first 2 tosses. No 5. And then here I get 5s. No 5. And then here I get no 5. 5s. All right, so we can clean this up because in middle school we learned about exponents, and all 3 of these are the same number. So this is nothing more than 3 times 4 over 36 squared times 32 over 36. So here's the thing. Many of you have already explained to me, you say, oh, Grady, I hate math. I don't like it. I have to take it. And that means you probably had bad experiences with math your whole life. And I get that. I understand. And so I know for some of you looking at this expression with these parentheses and exponents and all these numbers everywhere, it might be a little like overwhelming. And I get that. But I am telling you that it is possible for you to learn this. And it just takes time. You know, don't be afraid of the whiteboard. It ain't gonna hurt you. Think of it. Worst case scenario, C. Does anybody have a question about this?
No, but just wait until I take calculus with you next semester.
Are you taking it in the summer or are you taking it in the fall?
Fall.
It'll be fun.
Mm.
Calculus is the language of nature. You gotta learn.
Terrifying though.
No, it's not. Terrifying is the, you know, terrifying would be if you were homeless in New York City right now. That would be terrifying.
Holy shit, yeah.
Right. So, okay. So here's what we have. Let's go on the next page. We can put all this together, as scary as it is. So here's what we have. So what is the distribution we have? Well, we have number of 5s, and we'll use X to denote that. So what can we have? We can have 0, we can have 1, 2, or 3 5s. And then what is the probability we have them? We have to go all the way back to our first page. The probability we get no 5s is 32 over 36 to the third. But and then the probability you get 1 5 is 3 times 4 over 36 times 32 over 36 to the second power. The probability you get 2 is 3 times 4 over 36 squared times 32 over 36. This is kind of messy. Let me write this a little clearer. I'm gonna erase this. I mean, it's not gonna. I want it to be cleaner. I apologize. Hopefully you can adjust. So what's the probability that I get no 5s? Well, that we already computed is 32 over 36 to the third power. Probability to get 1 is 3 times 4 over 36 times 32 over 36 squared. The probability I get 2 is 3 times 4 over 36 squared, 32 over 36. And then lastly, it's 32 over 36. Excuse me, not 32 over 36. It's 4 over 36. So once again, what you see in this problem, much like with the coin toss, is there is all kinds of patterns hanging out here. Want to say hi? We got a visitor. This is Ricky. Ricky, say hi. Ricky, say hi. Say hi. No, you don't want to say hi? Okay, go play. So again, I know it looks frightening, but there's a pattern there. And it really, once we learn what that pattern is, it would not have taken us that long at all to do this particular problem. Does anybody have a question? Now, a good experiment for you to do is to calculate each one of those numbers, you know, on a calculator and see exactly how intuitive this probability distribution is. It's actually very much, it's very, what's a good word for it? It should match your intuition, and it should also provide you with some sort of, how do you say it? Motivation. Okay, so that's, again, if we're looking at the last two examples, the first one is a relatively simple one. This one was a little more complicated. But we're doing these things the long way instead of the short way. Any questions? All right, so what was the next topic we had? So the next topic was what we call the mean or the expectation of these things. And we did an example of that. Actually, we did two examples on Tuesday. So similar to the mean, another important number, and this is going to be a scary formula too, is what's called the variance. So the variance is very similar to variance we talked about before, but it is slightly different. So here's a definition. She's sliding down here. It's all right. Huh? No, they can't see her. They can hear her now. That's Ricky. That's fine. All right. So look, this is going to be a scary definition. We don't want it to be, and it's okay. The definitions with scary, using it actually is typically not that difficult. So got technical difficulties here. So let X be a random variable. And how do we denote its mean? We call its mean mu. It's like a U with a little, it's a Greek letter. That's the standard symbol for mean. So what is the variance? Well, we define the variance, and remember the variance is usually this sigma squared, as the following. So we have to use some scary notation. It's the following. It's, you take x sub 1 squared times the probability of x sub 1. And then you subtract, excuse me, then you add x sub 2 squared. Don't panic on these things yet. We'll remind you what they mean. In 1 second. And you do this for all, one of these days I'm going to figure this out. So you add up all the different outcomes of the random variables. So we'll say there's n of them. And then at the very end, you subtract the mean squared. And some people, for short, they'll write it like this: x px. And this is for short. So I mentioned this on Monday. Excuse me, I keep saying Monday, but on Tuesday. What is this Greek letter here? This is short for sum. And so what this means is you sum all values of x. So we did an example of this. This is, again, these kinds of things, these what we call the variance and the standard deviation and the mean. They're very important when you're analyzing data, particularly when you're trying to analyze data to determine how to make decisions. I don't want you to get too overwhelmed with this theorem, but if we do an example, what you'll notice is the homework problems, like 6 and 7, are actually not that difficult. You just have to write them down correctly. So let's do one of them to help ease your pain. Does anybody have a question? All right. So let's look at number 6, and then you guys can do number 7. So so let's look at this particular probability distribution. So for those of you who don't have it in front of you, the probability that x takes on 6 is 0.15. The probability that 8 people show up is 0.3. The probability that 10 people show up is 0.35. The probability that 12 people show up is 0.1. And the probability that 14 people show up is 0.1. So this is sort of like a very simple example of a real-world problem. Let's think of something. In this example, I'm talking about a tutor center, but let's think of something that's a little more intuitive. Imagine you are a grocery store, and assume it's not during a pandemic. You are, right? So if you're a grocery store and your job as the manager is to make a schedule for workers, Well, you're going to make some assumptions based on habits of shoppers. You're going to recognize that most shoppers aren't going to be there at 6:30 in the morning or at 11 o'clock at night. So you're likely going to have more people working at what we say peak hours than non-peak hours. So what grocery stores do is, well, especially now, is they have cameras and they have your Advantage cards. And what they do is they monitor how you shop so that they can, best supply the store, not just with food and groceries, but also with employees. Similarly, if you've ever been on the road and you drive over those rubber things that are on the road, and sort of like what they're doing is they're counting how much traffic roads get at any given time so that they can best think about how to program street signs or street lights, not street lights, traffic signals, I should say. So basically what we do is we try to set up some sort of experiment to determine certain things. And in this particular example, just imagine a make-believe tutor center studies how many people they have coming on a given day, and they want to make some sort of decisions based off that. So maybe they do a study, and they come up with this probability distribution, and what we want to do is study it. So that's what we're going to do. So what's the mean? So how do you compute the mean? Well, the mean is just x1 times probability of x1 plus x2 times the probability of x2, all the way up to the last one. There's 5 of them here, so I'll call it x sub 5, p of x sub 5. So the first thing is x can be 6, and what's that probability? It's 0.15. And then x can be 8, and that's probability 0.3. X can be 10, that's probability of 0.35. X can be 12, that's probability of 1. And then 14 times 0.1. Does anybody have a question about what I'm doing here? Because at this point, it just becomes how good are you at a calculator now? So if I go to a calculator, and I add these creatures up, it's 6.15 plus 8 times 0.3 plus 10 times 0.35 plus 12 times 0.1 plus 14 times 0.1. And if you plug this into a calculator correctly, I think I did, what you get is you get 9.4. So the way we might interpret that is that on any given day, we're going to see approximately 9.4 people show up. Does anybody have a question about this? All right, so that's the mean. So to get the standard deviation or the variance, depending on, I guess we get the variance first and then take the square root for the standard deviation. So to get the variance, we have to use the formula that we just wrote down. So the variance is, well, we have to sum this up slightly differently. We don't take just x, we take the squares. So this becomes 6 squared times 0.15 plus 8 squared times 0.3 plus 10 squared times 0.35 plus 12 squared times 0.1 plus 14 squared times 0.1, and then this is minus mu squared. So once again, you got to go to a calculator to figure all this out, or something like your friend Excel. So what I'm going to do right now is I'm going to go to the calculator and I'm going to square each one of these creatures. And if I do this, the first thing I get is I get 93.6, and then it's minus my 9.4 squared. If someone gets a different number, please, by all means, let me know. And if you do that, you get 5.24. So this is the variance. And then the standard deviation is equal to the square root of that. So what's the square root of 5.24? Again, that's for a calculator to help you with. And so you get, I guess it's not equal, it would be approximately 2.28. So this is exactly how you would compute the mean, the variance, and the standard deviation of a random variable. And if you actually spend time using these numbers, you'll see how they're important, when they're misleading, when they're not misleading. I tried to help illustrate that in the first homework and some of the stuff we did way back in the beginning of the semester. But it's really, these things are only going to be useful to you if you spend time with them. Other than that, they're just numbers that you calculate or don't calculate based on if you did the homework or not. Does anybody have a question? Comment, concern? Okay, so that was the first part of this problem. The next thing we want to know is what's the probability that fewer than 8 people visit? Well, we can look at that. So the probability that fewer than 8 what is this? Well, this is the probability that x is less than 8. But according to our chart, all that is that's the probability that x equals 6. And that is 1 or 0.15 based on our chart. That's the best I can do. Now, if I had a different distribution, perhaps I had one that used all visitors, 6, 7, 8, 9, 10, 11, it would be slightly different. And then similarly, fewer than 8 or greater than 12 would be this probability. It'd be the probability that X is less than 8 or X is greater than 12. And all that is 0.15 plus 0.1, which is 0.16. Does anybody have a question about that? A comment?
How are you adjusting to the whole pandemic thing?
Oh, my?
Yeah.
I am someone's paying attention. That's good. Thank you, Melanie. I am adjusting. I mean, it's weird. Can you hear my house right now?
Yeah.
I have a kid going crazy upstairs. I have Amy singing her the ABCs. She's running around naked. By the way, as Melanie, I'll call you up, pointed out, 0.15 plus 0.1 is not 0.16.
0.5.
Yeah, so you have to make sure you get your place value in the correct places. 0.15 plus 0.1 is, in fact, 0.25. Remember when you were a kid, you had to line up your decimal points?
Yeah.
Yeah. How's everybody else doing? Is everybody safe? I mean, this is wild. Just stay home if you can.
I still work in a grocery store, so I don't.
Are they paying you more? Or are they kissing your rear end for you?
Currently, no.
Who do you work for?
Shop and Save.
Oh, you better tell them to step their game up.
They're privately owned, so it's kind of hard to ask the owners to,
Yeah.
like Giant Eagle's corporate.
That's the same as our Giant. Well, my Giant Eagle is actually privately owned. It's not a corporate one. So they're under the same thing. Although I think we're going to be a little more fortunate in Pittsburgh. Don't forget, Pittsburgh's not dense like some of the other big cities. So we might not feel the wrath of this the way like New York and LA. Well, LA's actually doing okay too. Washington and New York's getting destroyed right now.
I'm just staying in my room because it's safe.
You could go out. You could go outside and walk. It's good. I mean, I've noticed more people outside walking than ever before, so that's good. It sucks that you can't do other stuff, but it'll be back to normal soon.
And I have 2 computer screens, so I'm perfectly happy in my room.
That's right. You know what? That's how I have it set up. That's why it looks like I'm not looking at you guys sometimes, because I'm looking at other monitors. It's not that I don't like you guys. Of course, none of you show your faces, which is fine. I don't give a damn. I don't need to see you guys. You're probably picking your noses and drinking whiskey and doing what other crazy things you should be not doing.
My dog just passed on my bed, so I'm just looking at her every so often.
Does anybody have a question?
I like your Grady pub thing in the back.
You like that, the O'Grady pub? This is my. Here, I'll give you guys a tour.
Yeah.
Here.
Oh, let's go.
Yeah, the pub thing looks really nice.
We'll give you a little tour of what we're witnessing. I think I can unplug this without anything bad happening. Yeah. So right now, can you guys see me? Or what do you see?
Wall.
Yeah, I see you.
You see
Hey,
me now?
Yeah.
You don't see the whiteboard anymore?
Nope.
All right, well, here we go. This is the new addition. We just had this done. This is the kids' one of their playrooms. Can you see all this shenanigans? This is where you just heard Ricky. She was going up and down this damn slide like a lunatic. This is the bookshelves. This is like my makeshift office right now. Someone's calling me. Who the hell's calling me? So this is, I hope there's no contraband anywhere here. It's a bathroom. You guys want to see a bathroom? Look how nice. Laundry room, right? This is it right here. This is the TV. There's a wounded rock star from yesterday. A couple of empty Dr. Peppers from the whiskey drinking. Yeah, this is a tour. There's my birthday present from Oh, there's a picture of fat me. Remember I told you guys I was fat? Here's a good picture of fat me. Look how fat I was years ago. That's a good one.
Oh.
Yeah,
Wow.
I know. That's what college does to you. You don't pay attention. And here, we'll even take you out back we'll take you outside. This is fun. Who'd have thought they were going to have all this fun? Look, here's the shed. Here's the construction zone. We had a deck built.
Wait, is that your truck?
What's that?
Your truck? That red truck?
I don't have oh, that's not mine. That's my neighbor's.
Uh,
That's the neighbor's truck. We just had a deck built, so now we have to get our driveway redone. This is just chaos, kids. But yeah, so it's a beautiful day. Listen, you guys have fun learning. I will post this to Canvas, and I don't remember what the due date is on. What is the due date on these homeworks? I don't remember.
7 is due the 31st.
Yeah, so you don't have to turn it in the 31st because we didn't really talk about the binomial yet, so you guys can delay it to Thursday.
okay. Did you already upload the last lecture?
It should be there. Oh yeah, I didn't. Here's what you need to do. Let me save the whiteboards just to make sure so I can upload them too. Okay, I think the whiteboard's saved. That's good. If you go to Canvas, what you'll see is I'm trying to share this webpage with you. It's giving me a hard time because it moved over here. If you go to where is my controls at? There we go. If I'm going to share the web page with you, so let's go back to this. If you go to Canvas, I'm going to have to maybe move some things around. Come on. So if you go to our, do you guys see the web page?
Mm-hmm.
If you click on on our web page, what you'll notice is if you go here to the one link pages, I'm going to have to make this more clear, but this was the only place I could upload it to. If you click on pages, you'll see a thing with lectures, and then it's right there.
All right.
So what I'm going to do is I'm going to try. I'm not going to try. I'm going to do it. I'll upload this lecture, and then I'll upload also these whiteboard pages. I'm going to make it just one PDF. That way you guys can have something to look at. Hopefully that helps. All right.
All right.
All right. Well, listen, I will let you guys go. And if you have any questions, don't hesitate to email me. And as I said, I'm going to try to get these grades updated as soon as possible. That's just, with everything happening, it's the least important thing, I think. I know you guys are going to say, no, it's not, but don't stress about your grades right now. Just stress about not getting the corona. All right, listen, I'm going to end this, and I will upload this later. If you have any questions, let me know, okay?
Thank you.
All right, guys, thank you. Take care. Be safe. Later.
Bye.
All right, see you.
Thank you.